Hi, everyone. My name is Chinwe. I'm going to be the session chair for this session. So without much ado, let's start with the first paper. And this is going to be by Yui Hao, and it's on creating foldable polyhedral nets. And 1 minute.
My name is Yue Hao. I'm a PhD student in computer science at George Mason University. My topic is creating foldable polyhedral nets using evolution control. Polyhedral nets are 2D unfolding of 3D meshes. They have many applications, including self-foldable structures using active material, or folding metal sheets using lasers, and of course, motor controllers for self-folding robots. So the challenge of creating these foldable polyhedral nets lies in the continuous foldability, whether we can find a continuous folding motion from the 2D configuration to the Go 3D configurations. Self-collision can happen even for simple shapes with small number of faces. Treat the nets as multi-linked robot, we can use a motion planner to plan a folding motion, which often involves multiple folding steps. Designing foldable nets is similar to designing a robot that would perform certain required motion, which is a very challenging problem. In current practice, researchers have to design unfolding, then use fabrication or simulation to check the foldability. If a collision is occurred, then the whole net need to be redesigned. This is frustrating because both finding the net and planning the folding motion are computationally expensive. In current practice, the nets are often designed manually using simple models. Our work is the first that design the nets by optimizing the foldability so that we're able to handle much complex models. So given a polyhedron, we can unfold it into different nets. Different nets have different foldabilities. We want to find the most foldable ones, like the one on the bottom, which is linearly foldable, that there you can find a linear folding path in the configuration space. We use a genetic algorithm to generate unfoldings. We first minimize the number of overlappings. Then we get a valid net. We optimize the foldability by minimizing the time for motion planner to plan the continuous motion. However, the problem of using motion planner as a fitness function for the genetic unfolder is that they are computationally expensive. And our solution is we construct a hypothesis fitness function, use all the geometric and topological features of the nets. These features are easy to compute. In our illusion control learning strategy, we have multiple hypothesis fitness functions for the unfolder to generate multiple nets. These small set of nets are used in motion planner to evaluate their foldability, and we have external optimizer to optimize the hypothesis fitness function using the evaluation. So this video shows the procedure of the optimization. In the first few iterations, the nets are mostly random. Gradually, you will see nets with similar topological features start to emerge. Then, in the final iteration, in the 30th iteration, all the nets converge to the most foldable one. So for complex models, we use a transfer learning technique to accelerate the optimization. So in this example, the Bunny 128 is optimized and by using a simplified model, Bunny 64, and we optimized Bunny 64 and use the result as initial guess for Bunny 128. The total time for optimizing the simplified model and the original model is still shorter than just optimizing the original model from the beginning. So this video will show various linearly foldable nets created using our method. The Bunny model has 128 faces, so the net has 127 degrees of freedom. On the right, we show the linearly foldable net, which means you can find a linear foldable path just by linear interpolation from the big start to Go configurations. On the right, this is arbitrary net. There are self-collisions throughout the linear path. You can still design a sophisticated motion planner to find the folding path. However, it's difficult for current the mechanism to execute those passes, especially for those self-folded material where they can only fold all hinges uniformly at the same time. Besides linear nets, we have some other nets for different applications and different even user-defined constraints. If you're interested, please stop by our poster. Thank you.
So our second speaker is going to be Noemi, and she's going to be talking about geometry-aware tracking of manipulability ellipsoids. Hopefully I didn't guess.
So I'm from the IDEAP Research Institute in Switzerland, and this is joint work with IIT. So let me introduce our work with an example. So as humans, we naturally align our posture in function of the requirement of the task that we have to solve. So for example, in archery, we naturally align our arm with the direction of the arrow for better performance. We also have other tasks, such as pushing or pulling an object, where the position of our hands is not the most important. What really matters is the posture of our whole body that will give us the force that is necessary to push or to pull the object. So as humans, our body posture greatly influences our task performance. In robotics, we also have an example where the posture is important. So for example, here the posture of the robot is adapted in function of the trajectory of the object to grasp. Another example where the humanoid posture is adapted in function of the position of the object to reach, or a kinematic analysis in function of the joint configuration in a writing task. So in robotics, the posture is also really important to fulfill the task execution. So a way to analyze the posture of the robot is via the so-called manipulability ellipsoid. So the kinematic manipulability ellipsoid is defined in function of the relationship between the task velocity and the joint space velocity. It indicates the ability of the robot to perform motion in any direction of the task space. So in this example, the robot will prefer to do a motion along the major axis of the manipulability ellipsoid. So in literature, we also have other examples of manipulability ellipsoid, such as the force manipulability or the kinematic manipulability. So to summarize, the manipulability indicates the preferred direction in which velocity, force, or acceleration may be performed at a given joint configuration of the robot. So we took inspiration from the classical inverse kinematic problem, where the goal is to find a Cartesian position, but in our case, we want to track a desired manipulability ellipsoid. So the manipulability is function of the Jacobian, which itself is function of the joint position. By computing the time derivative of this formula, we can find the change of manipulability over time, which is given by the manipulability Jacobian multiplied by the joint velocity. The manipulability Jacobian is a third-order tensor. So a tensor is a high-order matrix. So a matrix can be seen as a second-order tensor and a vector as a first-order tensor. Then by solving this equation for the joint velocity, we can find the following manipulability tracking formulation. So based on that formulation, we can now define controller to track manipulability either as main task on the left or as secondary task on the right. So in those examples, the desired manipulability is in blue and the current one is in red. So on the left, to track manipulability as main task is useful if we want to adapt or to change the robot posture before doing another task, such as position tracking. So you can observe here how the robot changes posture in order to match the desired manipulability ellipsoid as best as possible. Then if we have a main task, such as position tracking, and we want to do it with a desired manipulability profile, we can do manipulability tracking as secondary task by putting it in the null space term on the main task. So in this example, the main task is to hold the same end effector position, and you can see how the robot adapts its posture in order to match as best as possible the desired manipulability. So both our controller are geometry aware in their formulation. This is to take into account the fact that manipulability ellipsoids are symmetric positive definite matrices, so they belong to the to a Riemannian manifold. And this is important to have a good convergence of our controllers as we showed in the paper. So we perform an insertion task where the robot has to insert an electric cable into a plug. So we'll see here two different controllers. Both have position tracking as main task. The one with yellow dots has manipulability tracking as secondary task, and the one with blue dot doesn't have any manipulability tracking term. So the manipulability ellipsoid to follow here is a force manipulability, which main axis is aligned with the vertical axis to plug the electric cable. So this is to give the robot the maximum force in that direction. So we can see the difference of posture between the two controllers, and the one with manipulability tracking, the robot really adapts its posture to have the maximum force to plug the electric cable. So I'll be happy to answer any question at the poster session and to discuss more details with you. Thank you.
Okay, so our third speaker is Kirill Solovey, and he's going to be talking about the critical radius in sampling-based motion planning.
Good morning, and thank you for joining me. My name is Kirill Solovey, and I'm from Tel Aviv University. I'm going to present our work on the critical radius in sampling-based motion planning. This is joint work with Michal Kleinbord. In our work, we studied the theoretical properties of sampling-based planners that have the following three attributes. Those are planners that produce uniform random samples in Euclidean space. They connect between samples using a radius-based connection function, and they maintain either implicitly or explicitly a graph data structure. Previous work in this area has established that the connection radius of the following form, which is a constant times log n divided by n to the power of 1 divided by d, is sufficient for optimality, where n is the number of samples and d is the dimension. So by that I mean that when the connection radius is larger than this value, the algorithm is guaranteed to return a solution whose cost converges to the optimal value. In this work, we pose the following question. Can we further reduce the connection radius while still maintaining optimality? The motivation for that is that a smaller radius can reduce the running time of the algorithm and improve the performance. So in our work, we answer this question in the affirmative. We prove that the connection radius can be significantly reduced. So in particular, we show that the previous expression can be reduced to the following expression where the log n factor is replaced with a constant of 1. More formally, we prove that there exists a critical radius of the form constant times n to the power of -1 divided by d, such that the cost of the solution returned by the algorithm converges either to an optimal or a constant times optimal value, depending on the cost function, if and only if the connection radius used by the algorithm is larger than the critical value. So the implication is that now sampling-based algorithms can only need to connect only a constant number of neighbors for a given vertex rather than log n connections that was suggested by previous work, including the Karaman and Fazoli paper. So we first prove our result for the PRM and PRM star algorithms, and then we show how to extend these theorems to more modern techniques, which include RRGs, FMT stars, and other sampling-based planners, which even include sampling-based algorithms for multi-robot motion planning, in particular M-star, DRRT star. Second. We also validate our theoretical results in an experimental setting. In particular, we observed that a smaller connection radius that is actually close to the critical value that we obtained still yields high-quality solutions by the algorithm. We do mention that as the connection radius reduces and approaches the critical value, the success rate may be reduced as well. There is some small difference in the cost obtained by the original large radius and the smaller radii that follow from our work, but we noticed that by applying a smoothing technique to the produced paths, those differences in cost become negligible, as you can see in the plot behind me. So the difference in cost become negligible after we perform path smoothing on the result. Another interesting thing to note is that in some situations, using smaller connection radius, we can obtain better solutions in terms of the cost than the original larger radius for the same time budget and success rate. Okay, let me conclude by mentioning that we consider 3 different cost functions in this paper, which include bottleneck, length, and integral cost. And in addition to uniform random sampling, we also consider a new type of sampling, which includes grid graphs, which are then sparsified in a randomized manner. Okay, thank you for your attention, and I will see you at the poster session.
Okay, our last speaker is going to be Mike, and he's going to be talking about trajectory optimization on manifolds with applications to SO3 and R3X2.
Hi, I'm Mike. In this work, we propose a trajectory optimization for generalized manifolds, which we need a lot of differential geometry to define. And then we'll go through a couple application manifolds that we apply our method to. So first of all, differential geometry allows us to describe manifolds and how to take derivatives on manifolds. And we use this to be able to minimize the dimension of our trajectory optimization and also ensure that our description of our manifold is not actually interfering with our optimality description. So first of all, a definition of a manifold is some n-dimensional subset of Euclidean space, which is locally n-dimensional everywhere. So the classic example is a sphere. So a sphere can be embedded in 3-dimensional space, but everywhere on the surface, it kind of looks like a flat plane. And then the next definition is a chart. So we use a map from our local parameter space. So for example, a plane to a sphere. So this is an example of a stereographic chart, just from this little plane and animated to show what that looks like as you map to the sphere. But you can imagine there's many different ways to do this. So for example, latitude and longitude looks kind of like spherical coordinates, and stereographic coordinates look like that. And you want to make sure that your optimality condition is the same between the two of them. So the covariant derivative is a natural description that gives you this chart-dependent term that tells you actually how to, once you evaluate this, this is going to be invariant dependent on the choice of description of your manifold. So most of our work is in formulating this standard trajectory optimization, but all the classical optimization things are kind of replaced with these differential geometric versions of them. And then we show how to unfold that into sort of a classical trajectory optimization in the middle. And then we leverage existing techniques to transform that into something into finite parameters that you can actually optimize. So we do this by first searching for a kinematic path on the manifold, and then sort of using an algorithm to inflate a kinematic or a dynamically feasible chart or a region around that kinematic path, and then optimize over this sort of bubble region around a kinematic path. So this is an example of what it looks like on a sample manifold, is you end up with a sequence of charts that you need to glue together appropriately during your optimization procedure, and then you can use convex polyhedrons on the charts to sort of bound collisions. So you can ensure your resultant trajectory is going to be collision-free on the manifold. And this is in contrast to existing methods, which mainly when they deal with manifolds do some sort of projection step. So they treat the manifold in the high dimensional space and do projection during the optimization. There are a lot of direct methods which are optimizing directly on manifolds, but only for Rn. And so one of the toy examples we apply this to is a quadrotor that can aim a camera. So this creates a problem for a visual inertial odometry system where you have areas of poor texture. So we show how we can use this to sort of aim the camera around and avoid regions that are feature poor, and also minimizing optical flow, which is necessary for good tracking performance. Another example is we apply this directly to SO3. So SO3 comes up in a lot of different robotics applications, and we're able to optimize trajectories with and without out obstacles directly on the rotation group. So in summary, we've proposed this general method, and we end up formulating an optimization on the charts, which minimizes the dimension we need to optimize with a standard nonlinear optimization. And then we've shown a couple application manifolds. And then in the future, we want to apply this to several other manifolds to show this is a very generalizable method. And we've already done that for, so this is an example of planning for a quadrotor we did, where we switch between different charts to avoid singularities in SO3, and as well as extending to sort of a hybrid state where the quadrotor can reverse the direction of its propellers to fly upside down. And then we also have some more recent work where we've planned trajectories for a team of quadrotors in a fixed formation. So they're on the group SE3, and they need to reorient and avoid obstacles. I'd love to answer more specific questions at the poster session, and also Sakang is here to answer questions as well. Thanks.
So at this point, I'm going to have the 4 speakers come back up to the stage. And I think the floor is now open for questions. Yes, we have one at the back there. The blue mic.
I have a question for the last speaker.
Yes.
How are you dealing with the combinatorial challenge of swapping between different charts on your atlas within the trajectory optimization?
So do you mean the combinatorial problem? So if you have a large number of obstacles in your environment. So we first, during the kinematic search path, we're using an A*-based method. So that will only give you one method. So that restricts you to some homotopy class on the manifold to begin with. So you're not actually optimizing over all homotopy classes, which would be combinatorially intractable. So you're choosing a homotopy class to begin with.
Okay. The green mic.
So I have a question for the radius. So you said that the cost can be, the optimal value that you can get is sometimes the constant times the optimal cost. So is this, you have a bound on the constant, or if the constant is twice or thrice, how worse is the solution?
Oh, excellent question. So actually, we don't have a bound on the actual constant. But as I mentioned in the talk, we noticed that after you actually find the initial path and perform smoothing, there is no visible difference between the path that is produced with a smaller radius and the path that is produced with the original radius. But that's a different question. We should consider it in the future work, finding the actual constant. Thanks.
Green mic.
Follow up. Any idea why it is easier for the bottleneck cost function to actually get the optimum relative to the other case?
Yes. So the thing with a bottleneck cost is that as long as you stay in the vicinity of the optimal path, your cost is good, whereas for length cost, you need also to maintain, you can't do those movements from one point to another, which don't introduce any additional cost in the bottleneck cost function.
Any more questions? Yes. The green mic.
Okay. I have a question to Noemi. Computing the manipulability ellipsoid, I think you are using the inverse of J transpose J, or JJ transpose. I think that is not necessary to compute, and that if you compute it, it's not defined for the singular conditions, singular cases. So I think the ellipsoid can be defined without going through the inverse of that kind of matrix. Can you comment on that?
I don't really know another way to define it, but when we are close to singularity, we add a small singular value, and we can then compute the manipulability ellipsoid. And we also have, in all our controllers, we implemented singularity avoidance, so we don't have any problem to compute it.
Ellipsoid or manipulability measure is defined without using the inverse matrix. You might want to look at it. Also, the singularity avoidance was also implemented in 80s by one of Professor Yoshikawa's paper. And I also applied for the global optimization. So you might also want to look at it.
Okay, thank you.
Okay, the blue mic.
Thank you. So question on the foldable nets. So in most of the examples you showed, you were optimizing towards linear foldability. Is that always the right criteria, or are there cases where you want folding rate to be proportional to edge length or something else?
It really depends on your application. For some active foldable materials, the nets, all the hinges need to fold simultaneously or uniformly at the same speed. In that case, we need to reconfigure our foldability evaluator, which is the motion planner, and to make sure that for that particular application, we generated the uniformly foldable nets instead of the linear foldable ones. This is just an example. You can come to our poster. We have examples for other kind of foldable nets and to show. Thank you.
Okay, any more questions? So I had a question. Can you discuss in terms of, there's this slide I like having on my presentation, it's called like a dirty laundry slide. What were the challenges or the failures you faced while working on this particular research? That's a question for actually the four of you. It's an open question. You had challenges. I do research, so I know there's always some shortcomings or some failures you face that redirects your research. So what challenges did you face while working on this particular work?
I think the most challenge is to approach this problem, how do you define the problem? Because the research is not done before, and how do you actually define the foldability? How do you really to come up with your own approach to deal with the new problem?
Okay.
Maybe the more challenging part was to repose the math and try to solve them, to find the problem that we had to solve. Because the problem was well defined, so it was more computationally, I think.
For me, it was writing like thousands and thousands of lines of code, and finding like one sign error and that large chunk of thing is very challenging, especially with optimization-based work, where it's really hard to find little things.
Okay.
So for us, the challenge was to come up with a completely different approach to analyze those algorithms, because with previous techniques, you wouldn't be able to reach those conclusions as we did. So we needed to come up with something brand new.
Okay. Thank you. Do we have any other question? So I think with that, we'll come to an end to this session. Let's thank our speakers one more time. Okay. And I think we have a break now till about 10:30.